What if I told you the very fabric of reality might be stitched together by rules we don't yet understand? Picture the most bizarre paradox you've ever heard: Schrödinger's cat, alive and dead at the same time, and then realize that's just the tip of the quantum iceberg. Down in the depths of the universe, where black holes devour light and time bends like rubber, something even stranger is happening. The laws of gravity, the ones that keep our feet on the ground and the planets in orbit, seem to crumble when faced with the bizarre world of quantum mechanics. This isn't just a gap in our knowledge, it's a yawning chasm, one that could rewrite everything we think we know about space, time, and existence itself. For over a century, the greatest minds in physics have been locked in a silent battle between two titans: Einstein's theory of relativity, which governs the cosmos on the grandest scales, and quantum mechanics, the rulebook for the smallest particles in existence. Both work flawlessly in their own domains, but bring them together and the math implodes. This is the enigma of quantum gravity, the holy grail of modern physics. It's the missing piece that could unite the universe under a single set of laws, answering questions that sound like science fiction. What happens to information that falls into a black hole? Could space itself be made of tiny, vibrating strings? Are there hidden dimensions curled up smaller than an atom? Today, we're diving headfirst into 30 of the most astonishing theories that attempt to crack this cosmic code. From loop quantum gravity's pixelated view of spacetime to the holographic principle's mind-bending suggestion that our three-dimensional world might just be a projection, these ideas stretch the limits of imagination. Some are elegant, some sound almost magical, and a few might just be wrong, but each one represents a brave leap into the unknown, a testament to humanity's unshakable curiosity. So buckle up. By the end of this journey, you might never look at the universe the same way again. Imagine if space and time weren't smooth and continuous like a river, but instead made of tiny, indivisible building blocks, like the pixels on your screen, but far smaller. This is the radical idea at the heart of loop quantum gravity, one of the most promising attempts to marry Einstein's relativity with quantum mechanics. While general relativity paints spacetime as a seamless fabric, loop quantum gravity suggests it's more like a woven tapestry, stitched together by microscopic loops of energy. These loops aren't floating in space, they are space, forming a network so fine that if you could zoom in close enough, you'd see the universe as a shimmering web of connections. The theory's origins trace back to the work of physicists like Carlo Rovelli and Lee Smolin, who realized that if gravity has a quantum nature, spacetime itself must be quantized, broken into tiny, discrete chunks. Think of it like flipping a switch from analog to digital. Instead of time flowing smoothly, it would tick forward in ultra-small steps, and distances would have a smallest possible measure, far tinier than an atom. This has mind-blowing implications. For instance, near the center of a black hole, where relativity predicts gravity becomes infinite, loop quantum gravity suggests something wild. Those tiny loops of spacetime could stretch like a spring, preventing the singularity from forming entirely. But the theory's real fireworks show happens when we rewind the cosmos to the Big Bang. General relativity hits a wall at that moment, unable to describe the universe's birth. Loop quantum gravity, though, offers a daring alternative. Instead of a singularity, the universe might have bounced. Picture a collapsing star rebounding like a squeezed rubber ball. In this scenario, our universe could be the aftermath of a previous one that contracted to an unimaginably dense state before springing back outward. Yet for all its elegance, loop quantum gravity isn't without puzzles. It struggles to explain how the pixelated structure of spacetime at the tiniest scales smooths out into the universe we see today. And while it's brilliant at describing space, incorporating time remains a thorny challenge. Still, it stands as a bold reminder that the answers to gravity's deepest secrets might lie not in the void, but in the threads weaving it together. Now, let's unravel something even more radical, a theory so ambitious it rewrites the building blocks of reality. String theory dares to suggest that every particle in the universe, from the quarks in your atoms to the photons racing across space, isn't a tiny dot at all, but an impossibly small, vibrating string. These strings aren't just humming any random tune, their vibrations determine what kind of particle they become. A higher pitched oscillation might give you an electron, while a deeper thrum could create a quark. It's as if the universe were a cosmic symphony, and the laws of physics are its sheet music. But here's where things get mind-bending. For the math of string theory to work, these strings can't just wiggle in the 3 dimensions we know. They need more 6 or 7 extra dimensions, curled up so tightly we'd never notice them, like the folds in a crumpled sheet of paper. Picture an ant walking along a telephone wire. From far away, the wire looks one-dimensional, but up close, the ant can circle around it, discovering a hidden dimension. String theory argues our reality might be just like that, full of hidden folds where gravity, normally the weakest force, could suddenly become dominant. This elegance comes with a tantalizing promise. String theory could be the theory of everything, uniting all 4 fundamental forces, gravity, electromagnetism, and the nuclear forces, under one mathematical roof. Imagine a grand piano that, with different keystrokes, can play every note in existence. That's the scale of string theory's ambition, yet there's a catch. Despite decades of work, no experiment has ever directly detected these strings or their extra dimensions. They're trillions of times smaller than anything our particle colliders can probe, leaving physicists stuck in a dilemma. Without proof, string theory risks becoming less of a science and more of a philosophy, a beautiful idea floating untethered from reality. Compounding the mystery is the theory's landscape problem. The equations don't point to one unique universe, but to a staggering 10 to the 500 possible universes, each with different laws of physics. Some might have stronger gravity, others no electrons, and a few could even have time flowing backward. This multiverse menagerie leaves critics asking, if string theory allows for everything, does it actually explain anything? Still, the theory's mathematical beauty keeps drawing explorers. After all, if it's correct, we might finally understand why the universe's constants, the speed of light, the charge of an electron, have the precise values they do. Perhaps those numbers aren't arbitrary, but the only ones that allowed strings to vibrate their way into galaxies, planets, and eventually curious minds like ours. What if everything you see, the stars, the planets, even your own hands, was just an illusion? A 3-dimensional movie projected from a flat, 2-dimensional surface. This isn't the plot of a sci-fi film. It's the heart of the holographic principle, a theory so bizarre it turns our understanding of reality inside out. The idea first emerged from an unlikely source, black holes. When physicists like Jacob Bekenstein and Stephen Hawking studied these cosmic monsters, they stumbled on a paradox. Black holes seem to destroy information, swallowing it forever, yet quantum mechanics insists information can never vanish. The solution: maybe the information isn't lost at all. Instead, it's smeared across the black hole's event horizon, the point of no return, like a cosmic etch-a-sketch preserving every detail of what falls in. This led to a wild leap. If a black hole's entire 3-dimensional interior can be encoded on its 2-dimensional surface, could the same be true for our universe? Enter Juan Maldacén's groundbreaking AD/CFT correspondence, a mathematical bridge between 2 seemingly unrelated worlds. On one side, you have a universe with gravity, curved by exotic shapes called anti-de Sitter space. On the other, a flat, gravity-free realm governed by quantum fields. Maldacén proved these descriptions are equivalent, like discovering that a poem and a painting, though utterly different, are secretly telling the same story. The implications are staggering. If true, our 3D reality might be a hologram. It's every detail, every galaxy, every thought encoded on a distant 2D surface we can't perceive. Imagine a library where each book is a single page, but when you open it, the words leap off and build a full, immersive world around you. That's the holographic universe in a nutshell. But how could this solve quantum gravity's riddles? For one, it suggests gravity isn't fundamental, it's an emergent force, bubbling up from the interactions of quantum bits on that hidden surface. Think of it like the pixels on your phone screen. Individually, they're just dots, but together they create the illusion of depth and motion. The holographic principle flips the script on Einstein's spacetime, treating it not as the stage itself, but as the performance. Critics argue the theory's experimental proof remains elusive after all. How do you detect a cosmic projector screen that might lie at the edge of the universe? Yet supporters counter that the math's elegance is too compelling to ignore. And if they're right, the very nature of existence might be far stranger, far simpler, and far more beautiful than we ever dreamed. While loop quantum gravity visualizes spacetime as a network of interwoven loops, and string theory imagines tiny vibrating strings, there's another contender in the quantum gravity arena that takes a strikingly geometric approach. Picture spacetime not as threads or musical notes, but as a vast cosmic mosaic, an intricate patchwork of tiny triangular tiles that shift and rearrange according to strict rules. This is the essence of causal dynamical triangulations, a theory that slices the universe into microscopic geometric chunks to tame the chaos of quantum gravity. Unlike smooth, continuous spacetime in Einstein's relativity, this model treats the fabric of reality like a digital animation, where each frame is built from triangular building blocks specifically, four-dimensional analogues of triangles called simplices. These aren't just static pieces, they dynamically connect in ways that respect causality, meaning cause always precedes effect. Imagine a sprawling domino setup where each piece can only topple in one direction, ensuring time never loops back on itself or splits into paradoxes. This strict rule prevents the theory from generating bizarre, crumpled spacetime configurations that plague other quantum gravity models. The real magic of this approach lies in its ability to emerge smooth spacetime from the chaos of these tiny triangles. At microscopic scales, the universe looks like a roiling quantum foam, but zoom out, and the triangular patches blend seamlessly into the curved spacetime we know from general relativity. It's like watching a pointillist painting resolve into a clear image as you step back, an elegant solution to how quantum discreteness gives way to classical smoothness. Where loop quantum gravity struggles to incorporate time, causal dynamical triangulations bake causality into its foundation. Each triangulation step follows a strict sequence, creating a natural arrow of time without needing extra assumptions. This has led to some startling simulations. When researchers let these triangulated universes evolve on supercomputers, they spontaneously generate structures resembling our own expanding cosmos, complete with something akin to dark energy. Yet the theory isn't without its skeptics. Some argue its rigid geometric rules feel artificial compared to the organic flexibility of string theory or loop quantum gravity. Others note it hasn't yet reproduced all of general relativity's predictions, but as a daring blend of geometry, quantum physics, and cosmic storytelling, it reminds us that sometimes the universe's deepest truths might be hiding in plain sight, written in the angles of spacetime's smallest tiles. What if gravity isn't the unruly force we've struggled to quantize, but a puzzle missing just one crucial piece, a secret behavior hiding in its most extreme moments? That's the hope behind asymptotic safety, a daring quantum gravity theory suggesting that gravity might not be fundamentally chaotic at all. Instead, it could become mathematically tame at unimaginably high energies, like those near black hole singularities or the Big Bang. The key lies in a concept called renormalization, a way physicists clean up equations that would otherwise spit out infinite, nonsensical results. In quantum field theory, renormalization works beautifully for forces like electromagnetism, but gravity stubbornly resists it. That is, unless gravity's strength, its so-called coupling constant, stops changing at ultra-high energies and locks into a fixed value. Picture a reckless river finally calming as it reaches a waterfall's edge, its turbulence settling into a predictable pattern. That's the asymptotic safety scenario. Gravity's wild quantum fluctuations could stabilize just in time to prevent infinities from wrecking the equations. This idea traces back to physicist Martin Reuter, who in the 1990s applied a mathematical tool called the renormalization group to gravity. Normally, this tool helps physicists see how forces behave at different energy scales. Reuter's calculations hinted at something remarkable. Gravity might have a hidden safety net, a fixed point where its behavior becomes predictable even at Planck scale energies, where space and time lose all semblance of classical order. If true, it would mean that what appears as chaos is actually a higher form of structure, a cosmic failsafe woven into the laws of nature. The implications are profound. Asymptotic safety could dissolve the terrifying singularities inside black holes, replacing them with dense but finite cores where gravity's laws hold firm instead of breaking down. No more infinitely dense points of no return, just an extreme but calculable state of matter. Similarly, the Big Bang might not be the universe's absolute beginning, but a moment of maximum compression before a natural rebound, much like loop quantum gravity's bounce scenario. Yet the theory isn't without hurdles. Proving asymptotic safety requires grappling with fiendishly complex equations, and critics argue the fixed point might be a mathematical mirage, a trick of approximation rather than reality. But supporters point to tantalizing clues, like how asymptotic safety naturally predicts spacetime's fractal-like behavior at tiny scales, a feature echoed in other quantum gravity approaches. And unlike string theory's hidden dimensions or the holographic principle's cosmic projections, asymptotic safety offers a minimalist elegance. Gravity might not need exotic new ingredients to work quantum mechanically. It just needed us to look at it differently, to see the storm not as chaos but as a dance waiting to be decoded. The real test, of course, lies in experiments. If asymptotic safety is correct, subtle signatures might lurk in high-energy particle collisions or the echoes of gravitational waves. For now, it remains a bold bet on nature's frugality, a wager that the universe, in its infinite complexity, still prefers solutions that are at heart beautifully simple. What if gravity isn't a fundamental force at all, but something far more surprising, an illusion, a side effect of the universe's relentless drive toward chaos? This is the explosive idea at the core of emergent gravity, a theory championed by physicist Eric Verland that turns Newton and Einstein's grand legacy on its head. Forget bending spacetime or attracting masses. Verland argues gravity is more like the steam rising from a boiling kettle, a byproduct of deeper, invisible processes. His starting point, the second law of thermodynamics, which states that disorder, or entropy, always increases. From this single principle, Verland weaves a tapestry where gravity emerges from the frantic shuffling of quantum information, like the collective motion of a crowd creating the illusion of a wave. The theory's roots stretch back to an unexpected source, black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy, a measure of its hidden information, is proportional to the area of its event horizon. Decades later, Ted Jacobson took this further, proving that if you assume every patch of spacetime carries entropy, Einstein's equations of general relativity pop out automatically. Verland's genius was to flip this around. If entropy can produce gravity, maybe gravity was never fundamental to begin with. Picture a game of cosmic Tetris, where the way microscopic degrees of freedom arrange themselves creates the illusion of a force pulling apples toward the Earth. Here's where it gets even wilder. Verlin's math suggests that what we call dark matter, the mysterious substance thought to hold galaxies together, might not exist at all. Instead, the extra gravity we attribute to dark matter could be a side effect of emergent gravity's entropic pull. Imagine a ship leaving a wake in the water. The wake isn't a separate entity, just a consequence of the ship's motion. Similarly, galaxies moving through the universe's underlying quantum information field might generate gravitational effects we've mistakenly labeled as dark matter. Critics pounce on emergent gravity's lack of experimental proof after all. How do you test something as abstract as entropy-driven forces? And the math, while elegant, struggles to explain all galactic rotation curves without tinkering. But supporters counter that the theory's sheer audacity is its strength. If correct, it would mean the universe is even more interconnected than we thought, with gravity serving as a cosmic glue spun from the threads of information itself. Whether emergent gravity ultimately holds up or not, it forces us to ask a profound question. What if the forces we take as bedrock are just shadows of something deeper, something stranger waiting to be uncovered? What if the very coordinates we use to map the universe, the x, y, z of space and the t of time, stopped behaving like trustworthy signposts and instead started swapping places unpredictably? This isn't a glitch in reality's GPS. It's the startling premise of non-commutative geometry, a mathematical vision of spacetime so radical it makes quantum uncertainty look tame. Pioneered by mathematician Elaine Connes, this framework suggests that at the tiniest scales, space-time coordinates lose their conventional order. Multiply position A by position B, and you might get a different answer than position B times position a property called non-commutativity. Imagine trying to give someone directions where turn left, then walk forward, lands you somewhere entirely different than walk forward, then turn left. That's the kind of fuzzy, tangled geometry Connes proposes for the fabric of reality itself. The implications are profound. If space-time coordinates don't commute, the universe at Planck scale might resemble a grainy photograph where precise locations blur into statistical probabilities. You couldn't pin down a particle's position and momentum simultaneously, not because of measurement limits, but because space-time itself refuses to be nailed down. This isn't just mathematical whimsy. Non-commutative geometry has already shown eerie alignments with the standard model of particle physics. Connes and his collaborators discovered that by tweaking spacetime's algebraic structure, particles like quarks and electrons, along with their forces, emerge naturally from the equations, as if the universe's building blocks were hiding in the math all along. But where this theory truly shines is in the realm of black holes. When physicists apply non-commutative geometry to these cosmic voids, the usual singularity, a point of infinite density vanishes, replaced by a dense but finite core. Even more striking, the math reproduces Hawking's famous black hole entropy formula, suggesting a deep link between spacetime's fuzziness and the way black holes store information. Picture a black hole's event horizon not as a sharp boundary, but as a shimmering quantum veil, its non-commutative structure encoding data like a scrambled hard drive. Critics point out the theory's abstractness. It's heavier on elegant equations than experimental predictions. Yet supporters argue that its ability to unify gravity with the standard model, all while sidestepping singularities, makes it a sleeper hit in the quantum gravity arena. Whether non-commutative geometry is the final answer or just a stepping stone, it forces us to confront a dizzying possibility. The universe might not just have geometry, it might be geometry in its most wild and untamed form. Somewhere between the threads of loop quantum gravity and the mosaic tiles of causal dynamical triangulations lies a theory that strips spacetime down to its barest bones. a minimalist vision where reality is just a collection of events linked by cause and effect. This is the world of causal sets, where the universe isn't made of points, strings, or loops, but of irreducible atoms of causality, each connected to others in a vast, branching web of before and after. Forget smooth curves or geometric shapes. Here, spacetime is a raw sequence of happenings, like a cosmic domino trail where every tile represents a moment that can influence or be influenced by another. The theory's elegance lies in its radical simplicity. Instead of wrestling with the infinities that plague quantum gravity calculations, causal sets impose a single, ruthless rule: no event can be smaller than a certain size. This fundamental granularity, our smallest possible unit of spacetime, stops infinities dead in their tracks. Think of it like zooming in on a digital photo until you hit the pixels. There's no smaller to go. In causal sets, these pixels are events, and their relationships what caused what form the scaffolding of reality. A star exploding might trigger a supernova, which in turn illuminates a distant planet. Each link in that chain is a causal connection, building up the universe's history one domino at a time. Where other theories struggle to marry quantum mechanics with gravity by adding layers of complexity, causal sets take the opposite approach. They ditch continuous spacetime entirely, arguing that what we perceive as smooth geometry is just an emergent illusion, a statistical blurring of countless discrete events. Picture a pointillist painting. Up close, it's just dots, but step back, and the dots blend into a seamless image. Similarly, causal sets suggest that Einstein's curved spacetime isn't fundamental. It's the large-scale average of a universe built from causal handshakes. The theory's boldest claim: time might not flow at all. In a causal set, the past and future are fixed, a permanent network of relationships, and what we experience as the present is just our path through this frozen structure. Imagine a novel where every page already exists, but reading it creates the illusion of a story unfolding. Causal sets treat time the same way. The universe is a completed tapestry, and we're just tracing the threads. Yet for all its philosophical allure, causal sets face stiff challenges. How, for instance, does this minimalist framework reproduce the precise curvature of spacetime described by general relativity? And can it account for quantum weirdness, like particles being in two places at once? Supporters point to tantalizing hints, like how the random growth of causal sets, adding new events probabilistically, can approximate a universe that looks at large scales like ours. But without experimental evidence, the theory remains a compelling thought experiment, a reminder that sometimes the deepest truths are hidden not in complexity, but in the spaces between. There's a universe where spacetime isn't the stage, it's the aftermath, a shadow cast by something deeper and far more elegant. This is the bold vision of twistor theory, a mathematical framework dreamed up by physicist Roger Penrose that flips conventional physics on its head. Instead of starting with spacetime and building particles within it, Penrose's twistors suggest that spacetime itself might emerge from a hidden, more fundamental reality, a network of abstract geometric objects called twistors. Imagine trying to describe a rainbow by analyzing the paint on a canvas, only to realize the colors aren't pigment at all. They're the reflection of light you weren't seeing. That's the kind of paradigm shift twistor theory demands. These twistors aren't particles or strings. They're intricate mathematical entities that encode both a point in spacetime and the direction of a light ray passing through it. Think of them as cosmic knitting needles weaving together the fabric of reality through their intersections. When countless twistors interact, their collective geometry generates the spacetime we perceive, like the 3D illusion created by a hologram's 2D patterns. This approach isn't just philosophically daring, it's magnetically practical. Twistor equations simplify notoriously messy calculations in particle physics, turning pages of tangled algebra into sleek geometric operations. For instance, scattering amplitudes, the probabilities of particles colliding and rebounding, often resemble mathematical labyrinths in standard frameworks. But in twistor space, they collapse into elegant, visualizable shapes, as if the universe prefers to solve its own puzzles with origami. Where twistor theory truly shines is in its potential to bridge quantum mechanics and gravity. By treating spacetime as secondary, it sidesteps the infinite singularities that plague other quantum gravity models. Black holes, for example, might not be chaotic pits of crushed dimensions but smooth transitions in twistor geometry, like a flaw in a tapestry that, when viewed from the right angle, isn't a flaw at all. Even more tantalizing is the theory's link to M-theory, string theory's enigmatic cousin. Some physicists speculate twistors could be the alphabet underlying both, a shared language for the universe's deepest laws. Yet for all its beauty, twistor theory remains a work in progress. Critics point to its lack of a clear mechanism for how everyday spacetime condenses from twistor interactions, like admiring a recipe that hasn't yet produced a cake. And while it simplifies certain equations, others, like those describing massive particles, not just massless light rays, stubbornly resist its elegance. Still, Penrose's vision endures as a reminder that sometimes the most profound truths emerge when we stop asking how the pieces fit and start asking why we assumed they were pieces to begin with. What if the threads of spacetime weren't just loops, but a dynamic, ever-changing field, one that hums with the same mathematical rhythms as particles and forces? That's the leap group field theory makes, taking loop quantum gravity's intricate fabric and weaving it into something even more fluid. While loop quantum gravity imagines space as a network of interwoven loops, group field theory steps back and asks, could spacetime itself be a kind of quantum field, vibrating not in 3 dimensions, but on a strange, abstract landscape called a group manifold? Picture a symphony where every note is a tiny loop of space, and the entire composition is governed by harmonies only mathematics can describe. At its core, group field theory builds on loop quantum gravity's spin networks, those tangled webs where each thread carries quantized chunks of area and volume. But instead of treating these networks as static, the theory lets them dance. It imagines spacetime as a bubbling quantum foam where spin networks emerge from the interactions of an underlying field, much like particles popping in and out of existence in quantum field theory. Think of it as upgrading from a fixed mosaic to a living, shifting kaleidoscope. The tiles aren't just laid out, they're constantly rearranged by deeper rules. The magic happens when these abstract group fields, mathematical objects tied to symmetries like rotations, start interacting. Just as electrons exchange photons to create electromagnetic forces, group fields exchange quanta of space, stitching together the universe moment by moment. The theory's equations describe how these exchanges can spontaneously generate the very structure of spacetime, like a cosmic game of dominoes where each fall births a new piece of reality. But how does this quantum chaos smooth out into the spacetime we recognize? Here's where the continuum limit comes in. At microscopic scales, group field theory's universe is a frothing sea of disconnected fragments. Yet as you zoom out, these fragments coalesce like individual brushstrokes blending into a painting. The theory's greatest triumph is showing how this transition from discrete quantum chunks to the smooth, curved spacetime of Einstein's relativity might emerge naturally. It's as if the universe has a built-in smoothing algorithm, turning noise into symphony. Critics point out the theory's mathematical complexity, with some equations so intricate they've only been solved in simplified models. Yet its potential is staggering. By unifying the language of quantum fields with the geometry of spacetime, group field theory offers a bridge between loop quantum gravity and other approaches, like string theory's vibrating strings. It's a reminder that sometimes the deepest truths aren't found in the pieces themselves, but in the hidden rhythms that make them move. Black holes aren't just cosmic vacuum cleaners. they're laboratories for the most extreme physics imaginable, places where gravity and quantum mechanics collide in ways that rewrite the rules. One of the most shocking revelations came from Stephen Hawking in the 1970s when he realized black holes aren't truly black. They glow, radiating heat like a campfire ember. This Hawking radiation wasn't just a quirk. It implied black holes have temperature and entropy properties that belong to thermodynamics, not just gravity. Suddenly, these gravitational monsters were thermodynamic objects, their event horizons humming with quantum activity. The math was elegant, but the implications were mind-shattering. If a black hole emits radiation, it must also lose mass, slowly evaporating over eons. But here's the catch. Hawking's calculations suggested the radiation is purely random, carrying no information about what fell in. That violates quantum mechanics' sacred rule: information can't be destroyed, only scrambled. This became the infamous black hole information paradox, a puzzle so deep it forced physicists to question whether spacetime itself might have microscopic building blocks we've yet to grasp. Enter the firewall controversy. In 2012, a team of theorists proposed a brutal solution. At the event horizon, infalling particles wouldn't experience a smooth descent but a raging wall of fire, a quantum inferno burning away the information paradox. The idea was radical, suggesting Einstein's gentle spacetime curvature gives way to violent quantum turbulence at the horizon. Critics shot back. Firewalls would violate relativity's equivalence principle, the bedrock of general relativity. The debate raged for years, revealing just how little we understand about spacetime's microscopic structure. Yet beneath the chaos, black hole thermodynamics offers a tantalizing clue to quantum gravity. The fact that a black hole's entropy is proportional to its event horizon's area, not volume, hints at something profound. It's as if all the information inside is somehow encoded on the surface, a notion eerily similar to the holographic principle. Maybe spacetime isn't a continuous fabric but a patchwork of quantum bits, with black holes serving as cosmic Rosetta Stones, translating between gravity's language and quantum mechanics. The stakes couldn't be higher. Solving this puzzle might reveal how spacetime emerges from something deeper, exposing quantum gravity's hidden architecture. Until then, black holes keep whispering their secrets in the language of heat, entropy, and paradox, reminding us that the universe's most profound truths often lurk where our theories break down. Imagine if the entire universe began not as a singularity, but as a vast, frozen network where every connection between points was identical, like a perfectly symmetrical crystal. Then, in an instant of cosmic metamorphosis, that crystal shattered, and from its fractures emerged the rich, flexible fabric of spacetime we recognize today. This is the startling premise of quantum gravity, a theory that reimagines spacetime as a living, evolving graph made of quantum bits. At its heart, quantum gravity suggests that spacetime isn't fundamental. Instead, it's a dynamic web of connections between elementary units. Think of it like a cosmic social network where each node represents a quantum of information, and the links between them dictate how causality and geometry unfold. In the earliest moments of the universe, these connections might have been rigid and uniform, locking spacetime into a featureless, high-energy state. But as the cosmos cooled, a phase transition occurred, like water freezing into ice or a magnet losing its polarity. Suddenly, some links strengthened while others weakened or vanished entirely, creating the uneven, flexible structure we now call spacetime. This model offers a radical solution to one of quantum gravity's biggest headaches: how to reconcile the smooth, continuous spacetime of general relativity with the churning quantum uncertainty at microscopic scales. In quantum gravity, spacetime's smoothness is an illusion, a statistical average of countless flickering connections between nodes. Up close, the universe would look more like a rapidly changing lattice, with links appearing and disappearing in a quantum dance. Yet at macroscopic scales, these fluctuations average out, giving rise to the familiar four-dimensional continuum. One of the theory's most daring predictions involves the speed of light. In quantum gravity's early universe, before the phase transition, light might not have had a fixed speed at all. Instead, photons could have propagated instantaneously across the frozen network, a notion that challenges Einstein's bedrock principle. As the universe cooled and the graph's structure became more complex, light's speed would have settled into the constant we measure today. This could explain puzzling observations like the horizon problem, why far-flung regions of the cosmos appear eerily uniform in temperature, as if they were once in intimate contact. The theory also provides a fresh lens for black holes. Near a singularity where general relativity predicts space-time curvature becomes infinite, quantum gravity suggests something far stranger. The graph itself might unravel, its connections rewiring or breaking entirely. This could replace the infinite density of a singularity with a tangled quantum knot, where space-time's very structure becomes fluid and mutable. Critics argue that quantum gravity's abstract math makes it difficult to test, with few clear experimental signatures yet proposed. But supporters counter that its versatility, its ability to model both the birth of space-time and its extreme behavior under stress, makes it a compelling playground for theorists. After all, if the universe really is a cosmic graph, then every galaxy, every atom, might just be a pattern in the connections, a fleeting arrangement in an ever-shifting web of quantum relationships. And that raises a tantalizing question. What other phases might space-time yet transition into, given enough time or the right trigger? Eric Verland's vision of entropic gravity isn't just a tweak to Newton's laws. It's a wholesale reimagining of why apples fall and planets orbit. To grasp how radical this is, think of the universe not as a collection of objects governed by forces, but as a cosmic hard drive where gravity emerges from the way information is stored and shuffled. Verland's starting point is a profound parallel between gravity and thermodynamics, the science of heat and disorder. In the 1970s, physicist Jacob Bekenstein discovered that black holes have entropy, a measure of their hidden information, and that this entropy scales with the black hole's surface area, not its volume. Decades later, Ted Jacobson showed that if you assume every patch of spacetime has entropy, Einstein's equations of general relativity pop out automatically. Verland took these insights and ran with them, proposing that gravity isn't a fundamental force at all, but an entropic effect, a byproduct of the universe's relentless drive toward disorder. Here's how it might work. Imagine you place a particle near a massive object like Earth. According to entropic gravity, the particle doesn't feel a tug from some invisible force. Instead, it's responding to a gradient in entropy. The particle moves toward configurations where the entropy of the universe increases, much like a drop of ink spreading in water. The equations Verland derived from this logic don't just approximate Newton's law of gravity. They reproduce it exactly for weak gravitational fields. But the real bombshell came when he extended the idea to galaxies. Astronomers have long noted that stars orbiting galactic cores move too fast to be explained by visible matter alone, leading to the dark matter hypothesis. Verland's framework offers a daring alternative. What if there's no dark matter, just an entropic correction to gravity at galactic scales? His equations predict the same rotational curves without invoking invisible particles, a claim that sent shockwaves through astrophysics. Then there's modified inertia, or MHSC, a related idea that challenges Newton's first law. Proposed by physicist Mike McCulloch, MHSC suggests inertia isn't an intrinsic property of matter, but emerges from interactions with Unruh radiation, the faint heat a uniformly accelerating object perceives in empty space. In this view, when a star orbits a galaxy's outskirts, the extremely low acceleration alters its inertial mass, mimicking the effects of dark matter. While MHSC and entropic gravity differ in details, both share a revolutionary thread. gravity and inertia might not be fundamental, but emergent phenomena stitched into reality by deeper thermodynamic or quantum principles. Critics, however, aren't ready to discard dark matter just yet. They point to galaxy clusters like the Bullet cluster, where gravitational lensing reveals mass distributions that seem impossible without dark matter. Entropic gravity struggles to explain these observations cleanly. Traditionalists also argue that Verland's theory lacks a microscopic mechanism. How exactly does entropy produce gravity at the quantum level? Without experimental proof, entropic gravity risks being a beautiful mathematical metaphor rather than a physical theory. Supporters counter that the same was once said about atoms, and they're racing to find smoking gun evidence. Some propose tabletop experiments using ultra-cold atoms to detect entropic effects, while others scour galaxy surveys for deviations from dark matter predictions. The debate cuts to the heart of how science progresses. Entropic gravity isn't just a new theory, it's a philosophical shift, asking us to reconsider whether the forces we've taken for granted are just surface ripples on a deeper, stranger ocean. Whether Verland's bet pays off or not, his work forces us to confront a humbling possibility. Gravity, the force we thought we knew best, might still be hiding its truest nature in the shadows. At the heart of modern physics lies a tantalizing symmetry so perfect it could solve two of the universe's biggest mysteries at once. Supersymmetry, often called SUSY for short, proposes that every known particle has a hidden twin, a heavier superpartner lurking just beyond our current detection. This isn't just a whimsical doubling of nature's building blocks, it's a mathematical lifeline for quantum gravity. Think of it like a cosmic balancing act. The standard model's particles, quarks, electrons, photons, are unruly performers on a quantum tightrope, their wild fluctuations threatening to plunge calculations into chaos. But introduce their superpartners, quarks, selectrons, photinos, and suddenly the rope steadies, their combined contributions cancelling out the infinities that plague quantum gravity. The magic lies in how these superpartners differ from their twins. Fermions, the matter particles like electrons, have integer spin bosons as partners, while force-carrying bosons partner with half-integer spin fermions. This pairing isn't arbitrary, it's nature's way of restoring equilibrium. Take the infamous hierarchy problem. The Higgs boson's mass should be driven to impossibly high energies by quantum corrections, yet it's mysteriously light. SUSY superpartners would neatly counterbalance these corrections, like invisible hands steadying a wobbly table. Without them, the universe's fragility seems almost too improbable, a cosmic coincidence begging for an explanation. Now fold gravity into this elegant symmetry, and you get supergravity. Emerging in the 1970s, supergravity extends SUSY reach to include the gravitational force, treating the hypothetical graviton superpartner, the gravitino, as a key player. In some versions of string theory, supergravity isn't just an add-on. It's the glue that binds higher dimensional branes and explains how compactified dimensions might remain stable. Picture a multidimensional sculpture held together by invisible threads. Supergravity ensures those threads don't snap under quantum strain. Yet for all its theoretical grace, SUSY remains stubbornly invisible. The Large Hadron Collider, designed in part to hunt for superpartners, has yet to spot a single squark or photino. This absence isn't necessarily a death knell. SUSY particles might simply be heavier than current energies can probe, or they could decay too quickly to detect. Some theorists suggest we've been looking for the wrong signatures, or that SUSY is broken in ways that mask its effects at low energies. Others propose more radical ideas. Perhaps superpartners aren't particles at all, but excitations in a higher dimensional space. The suspense is palpable. If SUSY is real, its discovery would revolutionize physics, offering a unified framework for everything from dark matter. The lightest superpartner is a prime candidate to the universe's stability. If it isn't, we're back to the drawing board, forced to confront the unsettling fragility of reality without cosmic symmetry's safety net. Either way, sussy enduring allure reminds us that sometimes the most elegant solutions are the ones just beyond our grasp for now. What if the speed of light, that cosmic speed limit we've taken for granted, wasn't always the rule? That's the daring premise of Holographic gravity, a theory that rewrites Einstein's playbook by treating time and space as fundamentally unequal partners. Named after physicist Peter Holograph and inspired by condensed matter theorist Evgeny Lifshitz, this framework suggests that at ultra-high energies, like those near the Big Bang, spacetime isn't the smooth, relativistic fabric we know. Instead, time and space scale differently, like a movie where the frames and pixels adjust independently. This breaks Lorentz invariance, the symmetry that underlies special relativity, and opens a backdoor to quantum gravity without the usual mathematical nightmares. The theory's secret weapon is anisotropy, the idea that time and space can behave differently under certain conditions. Imagine stretching a rubber band. In relativity, it would stretch evenly in all directions, but in Holographic gravity, time might resist stretching while space warps freely, like a sheet of fabric with threads that only tug one way. This asymmetry lets the theory sidestep the vicious infinities that plague other quantum gravity approaches. Near a black hole singularity, for instance, time could slow to a crawl while space crumples, preventing the catastrophic infinite densities relativity predicts. It's as if the universe has a built-in failsafe, freezing time's flow before physics completely breaks down. One of the theory's most startling implications is a radical rethink of the Big Bang. Instead of a singular starting point, Holographic gravity allows for a bounce, a universe that contracted to a near singularity before rebounding, much like loop quantum gravity scenario. But here's the twist: the bounce isn't symmetrical. Time's unique scaling means the pre-bounce universe could have behaved wildly differently, with exotic phases where causality itself was distorted. Picture a cosmic pendulum swinging back, but on the return trip, gravity's rules subtly shift. Yet the theory isn't without its skeptics. Breaking Lorentz invariance is a high-stakes gamble. After all, relativity's predictions have been tested to exquisite precision. If time and space truly decouple at high energies, we'd expect faint relics of that asymmetry in today's universe, like variations in the speed of light or anomalies in cosmic rays. So far, no such smoking gun has been found. Worse, some versions of the theory struggle to reproduce general relativity's successes at low energies, like accurately predicting Mercury's orbit. Supporters counter that these challenges aren't deal-breakers, just growing pains. They point to tantalizing hints, like the theory's ability to naturally explain dark matter as a gravitational echo of the early universe's anisotropic phase. Others argue that Holographic gravity's mathematical simplicity, its avoidance of extra dimensions or abstract strings, makes it a dark horse in the quantum gravity race. Whether it ultimately holds up or not, the theory reminds us that sometimes progress lies not in patching old frameworks, but in daring to ask, what if the rules were never equal to begin with? Einstein taught us that the speed of light is nature's ultimate speed limit, but what if there's another, even more fundamental boundary woven into the fabric of reality? This is the spine-tingling suggestion of doubly special relativity, a bold reimagining of Einstein's masterpiece where not just light speed, but also Planck energy becomes an unbreakable cosmic rule. Picture a universe with two immovable pillars, one marking the fastest anything can travel, and another capping the maximum energy any particle can carry. Unlike standard relativity, where only light speed is sacred, this theory proposes a deeper symmetry, one where spacetime itself morphs to preserve both limits, no matter how fast you're moving or how energetic you become. The magic lies in how doubly special relativity tweaks Einstein's equations. Normally, energy and momentum are linked by simple, elegant relations like a sprinter's speed and stride length. But near Planck energy, a staggering 10 to the 19th gigaelectronvolts, these relations deform, subtly altering how particles interact with spacetime. This leads to modified dispersion relations, fancy jargon for how light and other waves might not travel exactly the same at all energies. Imagine shouting across a canyon. At normal volumes, your voice follows predictable acoustics, but scream loud enough, and the sound might warp or scatter unexpectedly. Similarly, ultra-high-energy gamma rays racing across the cosmos could arrive at Earth with tiny timing delays, their wavelengths stretched or compressed in ways standard relativity can't explain. Here's where cosmic detectives get excited. Gamma-ray bursts, those fleeting, brilliant explosions in distant galaxies, act as perfect test subjects. These bursts unleash photons across a jaw-dropping energy range from radio waves to gamma rays. If doubly special relativity is correct, the highest energy gamma photons should lag slightly behind their lower energy siblings, their journey through space-time subtly hampered by Planck scale effects. Astronomers have scoured years of gamma-ray burst data for precisely these telltale delays. Some observations, like those from the Fermi Gamma-Ray Space Telescope, hint at anomalies consistent with the theory's predictions, though the evidence isn't yet conclusive. But the theory's implications stretch far beyond astronomy. If Planck energy truly is a universal boundary, it could reshape our understanding of black holes. At a singularity's heart, where densities and energies theoretically soar to infinity, doubly special relativity might step in like a cosmic bouncer, enforcing a finite maximum. No more infinite curvatures, no more physics-breaking singularities, just a dense Planck energy core where space-time, though fiercely warped, remains mathematically tractable. Yet for all its elegance, doubly special relativity isn't without controversy. Critics argue that breaking Lorentz invariance even gently risks violating cherished principles like causality. Others note that alternative explanations, like interstellar dust subtly slowing high-energy photons, could mimic the theory's effects. And then there's the elephant in the room. If Planck energy is so fundamental, why haven't our particle colliders, slamming protons together at teraelectronvolts, spotted even a whisper of these effects? Supporters counter that we're still orders of magnitude shy of Planck energy, like trying to hear a pin drop in a hurricane. What makes this theory so electrifying isn't just its potential to tidy up quantum gravity's loose ends. It's the audacity to suggest that relativity, one of science's most battle-tested frameworks, might be the tip of a deeper, richer iceberg, one where the universe's rules flex and adapt, ensuring that no particle, no matter how mighty, ever cracks Planck energy's vault. Whether doubly special relativity ultimately holds up or not, it dares us to rethink a question we thought Einstein had settled. Are there limits even to the laws of physics themselves? Imagine if spacetime wasn't about distances or angles, but about pure shape, a cosmic sculpture where only the relationships between objects matter and the background geometry fades into irrelevance. This is the radical core of shape dynamics, a theory that dares to rewrite Einstein's general relativity by ditching spacetime's traditional scaffolding and focusing solely on how matter shapes the universe's contours. Forget curved manifolds and metric tensors. Here, the universe is a dynamic puzzle where every piece's position is defined only relative to others, like a celestial game of connect the dots with no fixed canvas. The theory's origins trace back to a simple but profound question. Why does time feel so different from space? In general relativity, time is just another dimension woven into spacetime's fabric, yet quantum mechanics treats it as a mere parameter, an external ticker against which probabilities unfold. Shape dynamics bridges this divide by demoting spacetime's geometry to a secondary role and elevating conformal geometry, the study of shapes and angles independent of size, to primacy. Picture a deflating balloon covered in dots. As it shrinks, the distances between dots change, but their relative arrangement stays the same. Shape dynamics argues that this arrangement, the pure relational structure, is what's truly fundamental, with time emerging as a measure of how these shapes evolve. One of the theory's most startling insights is its resolution of the problem of time in quantum gravity. In traditional approaches, time vanishes at the Planck scale, leaving physicists to wonder how the universe's clock even started ticking. Shape dynamics offers an elegant solution. Time isn't a background parameter, but a consequence of the universe's changing shape. Think of a symphony where the music's flow isn't dictated by a conductor's baton, but by the instrument's interplay. Similarly, time emerges from the cumulative shifts in matter's configuration, a cosmic rhythm arising from pure relational dynamics. This shift in perspective has dramatic consequences for black holes. Near a singularity, general relativity predicts spacetime's curvature becomes infinite, but in shape dynamics, there's no background geometry to blow up. Instead, the singularity might dissolve into a reshuffling of relational data, like a tangled knot that reconfigures without ever pulling infinitely tight. Even more intriguingly, shape dynamics naturally avoids the infamous firewall paradox at black hole horizons, since the theory's foundational principles forbid the violent discontinuities that firewalls demand. Critics point out that shape dynamics hasn't yet reproduced all of general relativity's successes, like the precise bending of light around stars. Yet its proponents counter that the theory's relational framework could unify quantum mechanics and gravity in ways Einstein's geometry-centric approach struggles to. After all, quantum mechanics is already deeply relational. Particles have no intrinsic properties, only correlations between measurements. Shape dynamics might be the missing lens that brings both theories into focus, revealing a universe where spacetime isn't the stage but the dance itself. Einstein's general relativity paints gravity as the curvature of spacetime, a smooth, geometric dance where planets and stars bend the stage they move across. But what if that stage isn't just warped? What if it's also twisted, like a cosmic ribbon writhing under unseen forces? This is the provocative twist, literally, introduced by quantum Einstein-Cartan theory, a bold reimagining of gravity that adds a new ingredient to Einstein's equations, torsion. While traditional relativity treats spacetime as a supple fabric bending under mass and energy, this theory suggests spacetime might also spiral, its geometric threads knotting and kinking in ways that could finally bridge the gap to quantum mechanics. The key lies in the peculiar behavior of fermions, particles like electrons and quarks that make up matter. In standard general relativity, fermions are awkward guests. They obey quantum rules but must squeeze into a classical spacetime mold. Quantum Einstein-Cartan theory welcomes them properly by letting spacetime twist in their presence. Picture a spinning top on a rubber sheet. In Einstein's version, the top just dents the sheet. But with torsion, the sheet also twirls around the top, mirroring its spin. This twisting isn't just cosmetic, it's gravity's quantum signature, a geometric fingerprint left by particles that refuse to sit still. Where the theory gets truly revolutionary is in its implications for the early universe. Torsion doesn't just tweak gravity, it supercharges it. Under extreme densities, like those during cosmic inflation, torsional forces could have generated repulsive gravity, a kind of cosmic anti-spring that violently propelled spacetime apart. This isn't just wild speculation. The math shows torsion can mimic the effects of dark energy, offering an alternative explanation for the universe's accelerated expansion. Imagine twisting a wet towel so tightly it snaps back with a splash. In the infancy of the cosmos, torsion might have been that explosive recoil, inflating the universe far faster than light. But the real magic happens when you zoom into the quantum realm. torsion provides a natural cutoff for the infinites that plague quantum gravity calculations, like a built-in regulator preventing spacetime from crumpling into nonsensical singularities. Near a black hole's heart, where general relativity predicts infinite curvature, torsion could step in like a quantum bouncer, keeping the geometry frayed but finite. Even more tantalizing, the theory hints at a deep link between spacetime's twists and the quantum spin of matter, suggesting gravity and the Standard Model might share hidden DNA. Of course, no theory is without its skeptics. Detecting torsion demands observing effects trillions of times smaller than those in particle colliders, leaving experimental proof frustratingly out of reach for now. Yet the elegance of the idea keeps physicists hooked. If quantum Einstein-Cartan theory is right, then every electron spin, every quark's wobble, might be leaving invisible corkscrews in spacetime's fabric, a hidden helix of gravity's quantum code waiting to be deciphered. And that raises a thrilling possibility. Maybe the universe isn't just curved, maybe it's twisted too. What if the entire universe could be boiled down to a vast, ever-shifting spreadsheet, one where every cell hums with quantum possibilities? That's the startling premise of matrix models, a family of theories that strip physics to its barest bones, representing spacetime and matter not as strings or loops, but as colossal matrices, grids of numbers whose interactions generate reality itself. The most famous of these, the BFSS model, emerged in the 1990s as a radical simplification of string theory. Named after its creators Banks, Fischler, Schenker, and Susskind, this framework suggests that the dizzying complexity of strings vibrating in 10 dimensions might be distilled into a single, deceptively simple equation, a matrix quantum mechanics where spacetime isn't assumed but emerges from the dance of numbers. Picture a symphony orchestra tuning up before a performance. Individually, each instrument's notes sound chaotic, but as they synchronize, harmony emerges. The BFSS model operates similarly. Its matrices start as abstract numerical noise, but under the right conditions, their interactions spontaneously organize into structures that look suspiciously like the dimensions of spacetime. In this view, the three-dimensional world we perceive isn't fundamental. It's a collective hallucination, a pattern etched into the quantum static. Even more astonishing, these models suggest gravity might not be a force at all, but a statistical effect, like the way pressure emerges from countless molecules colliding in a gas. Where matrix models truly shine is in their knack for tackling black hole puzzles. The BFSS framework, for instance, can describe certain black holes as fuzzy blobs of matrix data, a far cry from the infinitely dense singularities of general relativity. Calculations within this model reproduce the Bekenstein-Hawking entropy formula, implying that a black hole's event horizon might be a holographic screen where matrix degrees of freedom encode the interior's information. It's as if the black hole's essence isn't trapped inside, but smeared across its surface in a quantum spreadsheet, each cell holding a fragment of the story. The ties to holography run deep. Juan Maldacén's AD/S/CFT correspondence, the holographic principle's mathematical backbone, finds unexpected parallels in matrix models. Just as AD/S/CFT links a gravity-filled universe to a flat quantum field theory, the BFSS model hints at a similar duality. Matrices operating in lower dimensions might holographically project the higher dimensional spacetime we experience. Imagine a painter creating the illusion of depth on a flat canvas. Matrix models suggest our universe's dimensions could be brushstrokes in a fundamentally lower dimensional masterpiece. Yet for all their elegance, these models aren't without hurdles. The simplifications that make them tractable also limit their realism. The BFSS model, for example, describes a universe with only 9 spatial dimensions, not the 10 or 11 of full-string theory. And while they excel at approximating certain extreme physics scenarios, like black holes in highly symmetric spacetimes, extending them to messy, real-world conditions remains a challenge. Still, their very existence is a revelation proof that even the most arcane aspects of quantum gravity might be reducible to something as humble as a spreadsheet cells, whispering that beneath the universe's grandeur, there's a rhythm of numbers waiting to be heard. If the universe could be frozen in a single instant and examined under a quantum microscope, it might not resemble a smooth continuum at all, but a bubbling, frothing sea of geometric fragments, each carrying a tiny piece of spacetime's memory. This is the vivid picture painted by spin foam models, the dynamic counterpart to loop quantum gravity's spin networks. While spin networks capture space's structure at a fixed moment, spin foams evolve these networks across time, stitching them into a four-dimensional tapestry where change itself is quantized. Imagine flipping through a flipbook where each page is a spin network, a snapshot of space's quantum geometry, and the rapid succession of pages creates the illusion of motion. Spin foams are that flipbook's quantum counterpart, but with a twist. The pages aren't passive images. They're interconnected by tiny, discrete leaps of spacetime, like the bubbles in a cosmic foam. The theory's brilliance lies in its ability to reconcile loop quantum gravity's granularity with Einstein's demand for covariance, the principle that physics should look the same to all observers regardless of their motion. Traditional loop quantum gravity struggles here, as its formulation relies on slicing spacetime into separate time and space components. Spin foams sidestep this by treating time and space as equals from the outset, weaving them into a unified fabric where each foam bubble represents a quantum of spacetime's evolution. Picture a hyper-detailed 4D printer building the universe layer by layer, with each layer's geometry determined by quantum rules. One of the theory's landmark achievements is its reproduction of the Bekenstein-Hawking entropy formula for black holes. By counting the number of spin foam configurations that correspond to a black hole's event horizon, physicists can derive its entropy, a stunning confirmation that this abstract framework captures real physics. Even more compelling, spin foams suggest that at Planck scales, spacetime might undergo quantum jumps, fleeting transitions where geometry rearranges itself like a kaleidoscope's mirrors. These jumps could resolve singularities, replacing black holes' infinitely dense cores with fuzzy yet finite quantum regions. But the path forward isn't without obstacles. Recovering full general relativity from spin foams remains a work in progress. The equations simplify beautifully in highly symmetric scenarios, like the interior of a black hole, but become fiendishly complex when describing the messy, inhomogeneous universe we inhabit. Critics also highlight the problem of the continuum. How does this foam of discrete quantum transitions smooth out into the spacetime we observe? Supporters counter that this is akin to questioning how atomic jitters average out into the stillness of a solid table. The answer may lie in coarse graining, a mathematical technique that blurs the microscopic details to reveal emergent patterns. What makes spin foams so captivating isn't just their technical prowess, but their philosophical audacity. They force us to consider that time, the most intuitive of dimensions, might not flow at all. Instead, it could tick forward in Planck-sized increments, each moment a new spin network linked to its predecessors by the foam's delicate structure. If true, our experience of time's passage would be as illusory as the motion in a film reel, a cosmic sleight of hand performed by quantum geometry's invisible hands. What if gravity seems weak not because it's inherently feeble, but because most of it is hiding in another dimension? This mind-bending possibility lies at the heart of the Randall-Sundrum model, a daring twist on string theory's extra dimensions that could solve one of physics' most nagging puzzles: why gravity is roughly 10 to the 39th times weaker than the other fundamental forces. The answer, according to physicists Lisa Randall and Raman Sundrum, isn't about gravity's strength, it's about location. Imagine you're in a room where someone's shouting from behind a thick curtain. Their voice would sound muffled, not because they're whispering, but because the curtain steals most of the sound before it reaches you. In this radical framework, our familiar three-dimensional universe is like that curtain, a membrane or brain, floating in a higher dimensional space called the bulk, where gravity's full force roams free. The model's elegance lies in its geometry. Unlike string theory's tiny, curled-up extra dimensions, Randall and Sundrum proposed a single warped fifth dimension, exponentially stretched like a cosmic funhouse mirror. Our brain sits at one end of this distortion while gravity's source, perhaps another brain, lurks at the far end. The warping acts like a gravitational dimmer switch. Particles like photons and quarks are stuck to our brain, so their forces feel strong, while gravity's field lines stretch across the bulk, diluting its apparent strength. It's as if a magnet taped to your desk pulls strongly on nearby paper clips, while a second magnet placed on the opposite side of the room barely affects them, even if both magnets are equally powerful. This setup isn't just theoretical sleight of hand, it makes testable predictions. If gravity leaks into the bulk, high-energy particle collisions could produce Kaluza-Klein gravitons, heavy cousins of the standard graviton that carry glimpses of the fifth dimension structure. The Large Hadron Collider has hunted for these telltale resonances, watching for sudden spikes in missing energy, potential signs of gravitons vanishing into the bulk. So far, no smoking gun, but the search continues. Even more tantalizingly, warped extra dimensions could leave fingerprints in cosmic phenomena. Some versions of the model predict micro-black holes, not planet-swallowing monsters, but vanishingly small ones that evaporate instantly, emitting showers of particles detectable as exotic radiation patterns. Critics argue the theory trades one mystery for another. What anchors the brains, and why is the bulk's geometry so finely tuned? Yet supporters counter that the same fine-tuning questions plague more conventional approaches. What makes Randall-Sundrum stand out is its audacious simplicity. By warping just one extra dimension, it sidesteps string theory's labyrinthine complexity while preserving its power to unify forces. And if future colliders or gravitational wave observatories catch whispers from the bulk, it could mean we're not just three-dimensional beings in a three-dimensional world. We're islanders on a vast, hidden sea, sensing only the ripples that reach our shores. Einstein's gravity works like a cosmic game of telephone. Matter tells spacetime how to curve, and curved spacetime tells matter how to move, all through local interactions where influence spreads smoothly from point to point. But what if gravity doesn't play by those rules? Enter non-local gravity, a radical reimagining where gravitational effects aren't confined to nearby regions, but can leap across spacetime in ways that make quantum entanglement look tame. The key lies in infinite derivative corrections, equations packed with terms that account for gravity's influence over vast distances instantaneously. Picture dropping a pebble into a pond and watching ripples spread outward except in non-local gravity. Some ripples might appear halfway across the pond before the original splash even finishes, as if the water had a memory of disturbances yet to come. This bizarre behavior isn't just mathematical whimsy. It could solve two of physics' thorniest problems. First, singularities, those pesky infinite densities at the hearts of black holes, simply vanish in non-local models. Normally, as matter collapses under gravity's pull, curvature grows without bound, culminating in a point where physics breaks down. But non-local gravity introduces a kind of cosmic buffer, where infinite derivative terms act like shock absorbers, spreading the collapse's effects across spacetime before they can pile up into a singularity. Imagine a crumpling piece of paper that, instead of forming a sharp crease, softens and stretches like taffy, distributing the stress evenly. The result: black holes might harbor dense, fuzzy cores instead of infinitely dense pinpricks. Second, non-locality could reconcile gravity with quantum mechanics by sidestepping their most violent clashes. Quantum fields love to fluctuate at all scales, generating infinite energies that warp spacetime beyond repair in standard models. But infinite derivative gravity smooths these fluctuations by weaving together influences from across the universe, like noise-canceling headphones for spacetime. A particle's wild quantum jitters might be countered by subtle tugs from distant regions, keeping the fabric of reality intact. This isn't just theoretical sleight of hand. Certain non-local theories reproduce Einstein's predictions at cosmic scales while deviating subtly in extreme environments, offering testable signatures, like altered gravitational wave patterns or anomalies in neutron star collisions. Critics argue that non-local physics feels uncomfortably like magic, violating our intuition about cause and effect. How can gravity's influence skip across light years without mediation? Supporters counter that quantum entanglement already shattered localities. Rain particles instantly influence each other across vast distances, so why shouldn't gravity follow suit? The theory's real test will come when next-gen telescopes probe black hole shadows or gravitational wave observatories detect echoes of these non-local whispers. Until then, it stands as a daring reminder. The universe might not just be stranger than we imagine, but stranger than we can imagine, at least until the next ripple in the pond arrives. What if the very threads stitching spacetime together aren't gravitational fields or quantum loops, but something far subtler, entangled quantum bits humming with information? This is the electrifying premise linking quantum information theory to gravity, where spacetime itself might emerge from the universe's most intricate game of telephone. At the heart of this revolution lies the ER=EPR conjecture, an idea so audacious it connects wormholes to quantum entanglement. Proposed by physicists Juan Maldeisner and Leonard Susskind, it suggests that two entangled particles, like the EPR pairs Einstein famously dismissed as spooky action at a distance, might be secretly linked by microscopic wormholes or Einstein-Rosen bridges. Picture two marbles on opposite sides of a table. In our world, they're separate, but beneath the tablecloth, an unseen tunnel binds them. If true, entanglement wouldn't just be a quantum quirk, it'd be the glue holding spacetime's fabric together. This revelation ties into a deeper truth. Entropy, the measure of disorder, might be spacetime's hidden architect. In quantum systems, entanglement entropy tracks how information spreads between entangled particles. Astonishingly, calculations show this entropy scales with area, not volume, mirroring black hole thermodynamics, where entropy depends on event horizon surface area. It's as if spacetime, like a hologram, encodes its secrets at boundaries, with every bit of entangled information adding a stitch to the cosmic tapestry. Quantum error correction, the same tech protecting qubits in quantum computers, could be nature's tool for weaving this tapestry. Just as error-correcting codes distribute information to shield it from noise, spacetime might store data redundantly across entangled networks, preventing cosmic glitches from unraveling reality. Recent breakthroughs in quantum computing add fuel to the fire. Google's Sycamore processor and IBM's quantum leaps have shown how entangled qubits can simulate complex systems, including toy models of holographic spacetimes. In labs, researchers have even observed wormhole teleportation, where quantum signals traverse makeshift wormholes in entangled systems. These aren't cosmic tunnels you could fly through, but mathematical proxies hinting at deeper connections. Imagine building a scale model of a bridge with toothpicks. It won't carry cars, but it reveals the principles of arch support. Similarly, quantum computers are testing whether spacetime's architecture follows the blueprints of entanglement. Critics argue these ideas hover at the edge of testability, relying on mathematical elegance more than empirical proof. Yet supporters point to the AD/CFT correspondence, where black holes in higher dimensions map to quantum systems on their boundaries, a hint that spacetime's structure might literally be information in disguise. If entanglement builds spacetime, answering whether we live in a quantum simulation becomes beside the point. We might literally be patterns in the universe's quantum hard drive. Black holes may be cosmic titans, devouring stars and warping spacetime beyond recognition. But what if we could recreate their most exotic behaviors right here on Earth? That's the revolutionary promise of analog gravity, where physicists use controlled laboratory systems to simulate the extreme physics of event horizons and Hawking radiation. Take Bose-Einstein condensates, ultra-cold clouds of atoms chilled to near absolute zero, where quantum effects dominate. By manipulating these fragile quantum states with lasers, researchers can craft artificial event horizons, regions where atoms flow faster than the speed of sound, trapping ripples of sound waves just as a black hole traps light. In these experiments, something extraordinary happens. Pairs of quantum excitations, analogues to particles and antiparticles, pop into existence near the artificial horizon. One falls inward while the other escapes, mimicking Hawking radiation's telltale glow. The precision is uncanny. When scientists measure the escaping excitations, their spectrum matches Hawking's predictions with startling accuracy. It's as if we've bottled a black hole's quantum essence in a tabletop apparatus, revealing that Hawking's math isn't just theoretical. It's a universal feature of horizons, whether forged by collapsing stars or laser beams. But the real power of analog gravity isn't just replication, it's exploration. These setups let physicists probe questions too dangerous for astrophysics. What happens inside a black hole? In a lab, researchers can tweak parameters, adjusting flow speeds or interaction strengths, to simulate conditions near a singularity, testing how quantum effects might smooth out infinite curvatures. Some experiments even hint at solutions to the firewall paradox, showing how entanglement across horizons might preserve information without violating relativity. Beyond condensates, other analog systems are joining the hunt. Water waves in specially designed tanks can model spacetime's warping, while superconducting circuits emulate particle creation in curved spacetime. Each platform offers a unique lens, like a prism splitting gravity's mysteries into manageable wavelengths. Critics caution that analogs aren't black holes. They lack true gravity's grip, but supporters argue they're more than toys. They're proving grounds for quantum gravity's equations, revealing universal patterns that transcend any specific theory. And if Hawking's radiation shines in a lab, might other quantum gravity phenomena, wormholes, white holes, even baby universes, be waiting in the next experiment? The answer could rewrite not just how we see black holes, but how we see reality itself. Roger Penrose never met a cosmic paradox he didn't love, but his conformal cyclic cosmology might be his most audacious yet. Picture this: instead of a single Big Bang birthing our universe, time stretches endlessly in both directions, with each cosmic cycle ending not in heat death, but in an eerie metamorphosis where the universe's dying gasps become the spark for the next Big Bang. No multiverse, no singularity, just an infinite loop of rebirths, each connected through a mathematical sleight of hand called conformal rescaling. The idea hinges on a profound symmetry. As the universe expands toward absolute emptiness, its geometry becomes so stretched that distinctions like size and mass cease to matter. At this point, Penrose argues, the cold, featureless void of one cycle can be mathematically rescaled to match the hot, dense singularity of the next. It's like zooming in on a fractal until the pattern repeats, or watching a movie where the final fade to white is secretly the opening frame of the sequel. The smoking gun, according to Penrose, lurks in the cosmic microwave background, the afterglow of the Big Bang. His team claims to have spotted bizarre, circular patterns dubbed Hawking points, regions slightly warmer than their surroundings. These, he suggests, are the last evaporating vestiges of supermassive black holes from the previous universe, their death throes imprinted on our sky like cosmic graffiti. The logic is dizzying. In CCC, black holes never fully vanish due to infinite time horizons, leaving faint geometric echoes as universes recycle. Skeptics, however, aren't convinced. Independent analyzers argue these anomalies could just be statistical noise, and mainstream cosmology points out that inflation, the rapid expansion seconds after our Big Bang, should have erased any primordial fingerprints. Then there's the entropy problem. Thermodynamics dictates disorder must increase over time, yet our young universe began in a state of freakishly low entropy, like a pristine sandcastle untouched by waves. Penrose's solution, conformal rescaling, effectively resets entropy each cycle as particles lose their identities during the transition. Critics counter that this violates the second law's spirit, even if the math technically holds. Undeterred, Penrose frames CCC as a cosmic phoenix where death isn't an end but a transformation, a vision as poetic as it is polarizing. Whether future telescopes confirm Hawking points or consign them to cosmic pareidolia, one thing's certain. In a field obsessed with beginnings and endings, Penrose dared to ask, what if both are the same? Imagine if our universe was just a three-dimensional slice of something far grander, a floating island adrift in an unfathomable higher-dimensional ocean. This is the wild vision of brain cosmology, a theory where our entire cosmos isn't the whole story, but a brain short for membrane, a dynamic surface vibrating within a vast, hidden space called the bulk. While string theory dreams of tiny, curled-up extra dimensions, brain cosmology flips the script, suggesting at least one of these dimensions could be infinite, with our universe confined to its surface like a shadow cast on a cave wall. The real fireworks begin when these brains collide. Picture two sheets of paper drifting toward each other in a wind. When they meet, the impact could unleash enough energy to ignite an entire universe. This is the ekpyrotic scenario, a radical alternative to the Big Bang, where our cosmic beginning wasn't a singularity but a crash between neighboring brains. The collision's shockwaves would ripple through our brain, seeding matter, radiation, and the very structure of spacetime itself. What's even more mind-bending? This might not be a one-time event. Brain cosmology allows for cyclic models where universes bounce, eternally expanding, cooling, and eventually drawn back together by hidden forces in the bulk, only to collide and rebirth anew. But why would we be stuck on a brain in the first place? Here's where string theory's landscape comes into play. Just as particles like electrons can't escape the surface of a wire without immense energy, the fields and matter of our universe might be stuck to the brain by the very laws that govern them. Gravity, however, could be the lone exception leaking into the bulk, which might explain why it's so weak compared to other forces. Imagine living in a house where sound can't leave the walls, but faint echoes of distant music slip through the cracks. That's gravity in brain cosmology, a whisper from beyond our dimensional prison. Evidence for this radical idea is scant but tantalizing. Some models predict that brain collisions could leave imprints in the cosmic microwave background, subtle swirls or temperature variations that other theories can't explain. Others suggest that high-energy particle collisions might produce branons, exotic particles that dart into the bulk, vanishing from our brain in a puff of missing energy. So far, neither the Planck satellite nor the Large Hadron Collider has spotted these smoking guns, but the search isn't over. Critics argue that brain cosmology trades the mysteries of the Big Bang for even bigger ones, like what drives the brains to collide or what the bulk's physics even looks like. Yet supporters counter that it elegantly sidesteps the singularity problem, replacing infinity with a cosmic fender bender. And if true, it paints a humbling picture. Our universe might be just one page in an infinite dimensional book, its story written not in isolation, but in the margins where worlds touch. What if consciousness isn't just a byproduct of the brain's electrical chatter, but something far stranger, a quantum phenomenon where gravity nudges the boundaries between thought and reality? This is the provocative claim at the heart of orchestrated objective reduction, or a theory spun from the collaboration between physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their idea dances on the edge of quantum gravity and neuroscience, suggesting that the collapse of quantum states, the moment particles choose their definite properties, isn't random, but orchestrated by gravitational effects within the brain's microtubules. These microscopic protein structures, which form the skeleton of neurons, might be more than just cellular scaffolding. According to Orch or their quantum computers, their delicate superpositions collapsing under the weight of spacetime's curvature, generating flashes of conscious experience like fireflies in a dark room. The theory's roots dig deep into Penrose's earlier work on quantum gravity. In his book, The Emperor's New Mind, he argued that human cognition can't be purely algorithmic. There's a non-computable ingredient, something tied to the universe's fundamental physics. Pair this with Hameroff's research on microtubules, and you get Orch, or a proposal that consciousness arises when gravity-triggered quantum collapses in these tubules reach a threshold, creating moments of proto-consciousness that accumulate into full-fledged awareness. Picture an orchestra where each musician is a quantum vibration and gravity is the conductor, cueing them to play in harmony. The result, a symphony of subjective experience emerging from the quantum noise. But the scientific reception has been less than harmonious. Critics pounce on several fronts. First, the brain is warm, wet, and noisy, three things quantum systems despise. Maintaining coherent quantum states outside ultra-cold lab conditions is notoriously difficult, yet Orch claims microtubules somehow shield these states long enough to matter. Second, there's zero direct evidence that microtubules perform quantum computation, let alone that their collapses correlate with consciousness. Experiments searching for quantum effects in photosynthesis or bird navigation don't automatically translate to the brain's chaotic environment. And then there's the hard problem of consciousness itself. Even if quantum collapses occur, how do they feel like something? Orch skirts this by invoking Penrose's speculative math, where gravitational self-energy becomes the bridge between physics and qualia, a leap many find unconvincing. Yet the theory isn't without intriguing echoes. Some quantum biology research hints that biological systems might exploit quantum effects more than we thought. And Penrose's gravitational threshold, roughly one collapse per neuron every few hundred milliseconds, coincides with the timescale of conscious perception. Supporters also note that anesthetics, which selectively erase awareness, seem to target microtubules, hinting at a deeper link. Still, without falsifiable predictions or experimental validation, Orch remains a fringe idea, albeit one that dares to ask if the universe's deepest mysteries might be entwined with the very fabric of our minds. Whether Orch ultimately collapses under scrutiny or not, it forces a thrilling question. Could gravity, the force that shapes galaxies, also shape thoughts? The answer might lie not in the stars, but in the labyrinth of our own neurons, where spacetime's whispers could be the soundtrack of consciousness itself. Detecting the whispers of quantum gravity might seem like hunting for a single note in a cosmic symphony, but physicists are tuning their instruments with unprecedented precision. Take LIGO, the Laser Interferometer Gravitational Wave Observatory, which made history by capturing ripples in spacetime from colliding black holes. While LIGO primary mission is testing Einstein's relativity, its next-generation upgrades could sniff out subtler anomalies, hints that spacetime isn't perfectly smooth at Planck scales. Imagine listening to a violin while straining to hear the quantum crackle of the varnish. LIGO advanced detectors might spot minuscule deviations in gravitational waves that betray spacetime's granular structure. Then there's pulsar timing arrays, nature's ultra-precise metronomes. These spinning neutron stars beam radio waves with clock-like regularity, but if spacetime foams disrupt their signals, the pulses could arrive with Planck-scale jitters. Current arrays like nanograv are already sensitive enough to detect nanohertz gravitational waves, and future projects could push into regimes where quantum gravity's fingerprints might lurk in the static. It's like watching a flawless pendulum for decades, waiting for the tiniest, inexplicable quiver. Gamma-ray telescopes add another dimension. When distant blasts like gamma-ray bursts traverse the cosmos, high-energy photons should outpace their lower-energy siblings, unless spacetime's quantum texture treats all light equally. The Fermi Space Telescope has scoured bursts for these energy-dependent delays, probing whether light's speed remains constant at the universe's most extreme scales. So far, the results are inconclusive, but with each new burst, the net tightens. The challenge, Planck scale effects are absurdly faint, like trying to measure the width of a human hair from a light year away. Particle colliders would need energies a quadrillion times beyond the Large Hadron Collider's reach to directly produce quantum gravity phenomena. That's where clever workarounds come in. Tabletop experiments with ultra-cold atoms or superconducting circuits might amplify these whispers, while cosmological surveys could find statistical oddities in the universe's large-scale structure. The stakes couldn't be higher. Every null result narrows the path for theorists, forcing them to refine their equations. And if just one experiment catches a glimmer, a deviation in gravitational waves, a pulsar's timing hiccup, or gamma rays marching in lockstep, it could crack open quantum gravity's enigma, revealing whether spacetime is woven from loops, strings, or something stranger still. Until then, these experiments are the universe's most patient detectives, sifting through noise for the faintest signal of a deeper reality. The multiverse isn't just a sci-fi trope, it's a serious scientific possibility, one that quantum gravity might either validate or vaporize. Picture an endless foam of universes, each bubble inflating forever, birthing new bubbles with slightly different laws of physics. This is eternal inflation, the engine behind one flavor of multiverse, where quantum fluctuations in the early universe stretch spacetime so violently that regions pinched off into entire cosmoses. Now layer this with string theory's landscape, a dizzying 10 to the 500 possible vacuum states, each representing a unique universe with its own constants and particles. Suddenly, the multiverse isn't just plausible, it's practically unavoidable. But here's the twist: quantum gravity could be the glue holding this cosmic kaleidoscope together, or revealing it as a mirage. Take eternal inflation first. When spacetime expands exponentially, quantum jitters at the tiniest scales get magnified to cosmic proportions, seeding new universes like buds on a fractal tree. But what stitches these bubbles together? Some theorists propose quantum entanglement spanning multiversal boundaries, where entangled particles in separate universes remain weirdly linked, their fates intertwined even as their spacetimes drift apart. It's as if the multiverse is a vast quantum network with gravity, or its quantum counterpart acting as the router managing the connections. Others argue this is wishful thinking, pointing out that without a theory of quantum gravity, we can't even define how these universes might interact, let alone prove they exist. Then there's string theory's landscape problem. If every possible universe exists, how do we explain the bizarre fine-tuning of our own? Quantum gravity might offer an answer or deepen the mystery. In some frameworks, the wave function of the universe could branch eternally, with every quantum decision spawning new timelines. This many-worlds interpretation, when combined with string theory, suggests we're just one thread in an infinite tapestry of realities, each with its own version of gravity. But critics fire back. If the multiverse is unfalsifiable, if we can't observe or test these alternate realms, does it even qualify as science? Supporters counter that quantum gravity might leave fingerprints in our universe, like imprints of collisions with neighboring bubbles in the cosmic microwave background, or anomalies in the distribution of dark matter. The debate cuts to the heart of what science is. Is the multiverse a natural extension of quantum gravity's math, or a philosophical cop-out? Some argue it's no different from pre-Copernican astronomers placing Earth at the universe's center, another example of our bias toward uniqueness. Others see it as the ultimate humility. Our universe might just be a speck in an unthinkably vast ensemble where gravity's rules shift like sand. Until quantum gravity gives us the tools to peek beyond our cosmic horizon, the multiverse remains the most thrilling and frustrating maybe in physics. One thing's certain, if it's real, the universe just got a lot bigger. And if it's not, well, that's a mystery worth collapsing into. We stand on the edge of a precipice, peering into the deepest mysteries of reality, where the questions themselves threaten to unravel everything we think we know. Is space-time truly fundamental, or just a shimmering illusion emerging from quantum entanglement? How does information, once swallowed by a black hole's abyss, somehow find its way back out, defying the grim predictions of Hawking's original calculations? These aren't just academic puzzles, they're cosmic riddles that could redefine existence itself. The debate over spacetime's fundamental nature cuts to the heart of quantum gravity. For centuries, we've treated space and time as the immutable stage upon which the universe plays out. But what if the stage is the performance? Loop quantum gravity and spin foams suggest spacetime might be woven from discrete quantum threads, while string theory hints at higher dimensional fabrics vibrating beneath our perception. The holographic principle goes further, proposing that our 3D reality is a projection from a 2D surface, like a shadow cast by some deeper, hidden structure. Resolving this isn't just philosophical, it's practical. If spacetime isn't fundamental, then black holes, the Big Bang, even the arrow of time might need radical reinterpretation. Then there's the black hole information paradox, a problem so thorny it's pitted quantum mechanics against general relativity in a battle with no obvious victor. If information can't be destroyed, a cornerstone of quantum theory, then what happens when it vanishes beyond an event horizon? The firewall hypothesis, holographic encoding, and even emergent gravity offer competing solutions, each with staggering implications. Perhaps information isn't lost at all, but smeared across the horizon like cosmic graffiti, waiting to be decoded. Or maybe black holes aren't the end, but gateways to other universes, their singularities bursting open like seeds in a cosmic garden. The tools to crack these enigmas are closer than we think. Next-generation telescopes like the Laser Interferometer Space Antenna LISA will listen for gravitational waves from colliding supermassive black holes, potentially revealing echoes of quantum structure in spacetime's ripples. Meanwhile, quantum computers still in their infancy are already simulating toy models of holographic universes, testing how entanglement might knit spacetime together. And lurking on the horizon are tabletop experiments probing Planck-scale physics, where ultra-cold atoms or superconducting circuits might tease out gravity's quantum whispers. But the most tantalizing breakthroughs could come from where we least expect them. Dark matter's elusive nature, the accelerating expansion of the universe, even the startling uniformity of the cosmic microwave background, each could be a breadcrumb leading to quantum gravity's doorstep. The challenge isn't just finding answers, but learning to ask the right questions. Because if history teaches us anything, it's that the universe is always stranger, more elegant, and more connected than we dare imagine. The future of quantum gravity isn't just about equations. It's about rewriting the very story of reality. We've journeyed through a labyrinth of cosmic ideas, each more mind-bending than the last, where spacetime shatters into loops, strings, and holograms, where gravity emerges from chaos and black holes might hide universes. From the pixelated spacetime of loop quantum gravity to the vibrating symphonies of string theory, from the entropic whispers of emergent gravity to the holographic codes that could rewrite reality itself, one truth stands clear: the universe refuses to be simple. Every theory we've explored isn't just a wild guess, it's a torchlight in the dark, illuminating a different facet of quantum gravity's enigma. Some might clash, others might converge, but each dares to ask, what if we've been missing the forest for the trees? What's astonishing isn't just the diversity of these ideas, it's how they reframe the questions themselves. String theory's extra dimensions force us to confront whether our 3D world is the whole story. The holographic principle asks if reality is a projection, a cosmic sleight of hand. Causal sets strip spacetime down to its barest bones, while emergent gravity suggests the force we thought we knew might be an illusion all along. Even the failures are illuminating. When theories collide with paradoxes like firewalls or singularities, they expose gaps in our understanding that could be portals to something deeper. So where does that leave us? Spoiler alert, we don't have a winner yet, but that's the thrill of science in progress. Maybe the truth lies in one of these frameworks, or in something stranger still, waiting just beyond the edge of our equations. Personally, I'm torn between the elegant minimalism of loop quantum gravity and the audacious beauty of the holographic principle. But that's the fun part. You get to pick your own adventure. Which theory resonates with you? Is it the cosmic symphony of strings, the twisting tapestry of Einstein-Cartan, or something else entirely? Drop your favorite in the comments, because the next breakthrough might not come from a lab, but from a conversation like this one. Stay curious, stay bold, and remember, the universe doesn't owe us answers. It's up to us to keep asking better questions. Who knows, the ultimate theory of quantum gravity might be lurking in these very ideas, waiting for someone to connect the dots in a way no one's imagined yet. Until then, keep looking up and don't forget to question everything, even the ground beneath your feet. After all, it might just be an illusion.